I'm Hao-Chung Chen from National Taiwan University. I'm also jointly affiliated with the Honghai Faksang Quantum Computing Center. Can you hear me in the end? Not so. Okay, right now? How about now? Is it okay? Is it okay? All right. So today I will talk about achievability in one-shot quantum information theory. This is the outline of the talk. Firstly, I will describe the motivations and backgrounds and the fundamental questions in one-shot quantum information theory. Then I will review the existing methods for one-shot achievability. Then I will go to the proposed method and its implications. Then I will mention the applications of the analysis to other quantum information theoretic tasks and conclusions. Okay, let's start. In this talk, I will mainly focus on the classical communication over quantum channels. Suppose we want to send a uniform message taking values 1, 2 to the capital M through a quantum channel. We first encode it to a large quantum state. It could be several qubits on systems, say A1, A2 to the AN. Then each qubit suffers from independent and identical noise. We call this the IID product quantum channels. Then at the channel output, we perform a measurement to decode the message. Okay, and the well-known HSW theorem states that if the rate of coding defined in terms of the number of bits to be sent per channel is strictly smaller than the channel capacity, then the error probability of decoding will vanish as n goes to infinity. However, such an asymptotic setting is not very realistic in practice. First, since n has to go to infinity, we will require an arbitrarily large quantum processor to implement the encoder and the decoder. Second, an actual noise could be correlated among a few qubits. Third, even if the channel is independent, it might not be stationary, meaning that the noise acting on the first qubit might not be identical to the noise acting on the last qubit. So the spirit of one-shot quantum information theory is to consider the noise as the whole thing without imposing any specific structures on the channels, such as the IIDness. There are two fundamental questions to one-shot quantum information theory, especially for achievability. The first one is that given a message size m, what is the minimum error probability we can achieve? Here, the minimization is over all possible encoders and decoders. Second, how much information can we send to achieve an epsilon error probability? The logarithm of the largest such n is called the epsilon one-shot channel capacity. A general recipe for analyzing one-shot quantum information theory is the following. We first reduce a quantum information theoretic task to a one-shot quantum hypothesis testing problem. Then we characterize the operational quantities of interest, for example, like the largest message size, the minimum error probability, in terms of some quantum divergences, such as the hypothesis testing divergence, quantum Renyi divergences, smooth entropy, etc. And then we will also use the asymptotic expansions of those divergences for product states to evaluate how tight the one-shot bond is. The audience is referred to an excellent tutorial on one-shot quantum information theory by Marco, that's the QIP. Okay, the reduction to a quantum hypothesis testing problem is the main focus of this talk. How was it done previously? The existing works are mostly based on a powerful information spectrum method. Taking classical quantum channel coding as an example, where the channel takes a classical symbol as input and output a density operator rho bx. Then Hayashi and Nagaoka proved a useful operator inequality back in 2003. Here, I use the notation of the non-commutative quotient. It's not easy to see why this inequality works for achievability. It's not trivial at all to prove this operator inequality. Also, there are those coefficients there that may loosen the bonds. In 2019, Osquey, Mancini, and Wilde show that the Hayashi-Nagaoka operator in quality works as a quantum union bond. But still, it's not trivial at all to prove the quantum union bond, and also those coefficients are there. So the goal of this talk is to provide a conceptually simpler proof for one-shot achievability by directly using the predicable measurement. It turns out that the simple analysis gives tighter one-shot bonds and also streamlined proofs to many other quantum information theoretic tasks. Okay, let's go to the proposed method. And let me introduce a notation and some properties of it. First, I introduce a non-commutative minimum between two operators A and B as the greatest lower bound to A and B. Here, this order is the operator partial order, and the greatest is in the sense of trace. Holevo and Hellstrom in 1970s show that this non-commutative minimum is actually unique and has a closed form expression like this. The trace of it has an operational meaning in quantum hypothesis testing. This quantity is interpreted as the minimum error of discrimination between operators A and B. Please keep this in mind. I will use this interpretation throughout the talk. There are some properties. By definition, we can see that this quantity is monotonically increasing in its argument. It's also monotonically increasing under trace-preserving maps because the trace norm is contracted under trace-preserving maps, and there's a negation here. It's jointly concave in its argument, and we know there's a direct sum structure for the trace norm. They are all basic known facts. A nice upper bound was proved by Ordinatz et al. In 2008. It is also called the Hao-Chung Chen bound. An important technical tool in this talk is a lower bound to the non-commutative minimum by this form. Again, I use the non-commutative quotient here. Why is this true? It's easy to see for the commuting case because the minimum between two positive numbers is lower bounded by the parallel sum, namely the product over the sum. To give you a flavor of why this is true in the quantum case, let's consider a special case that A and B have equal trace, rho and sigma. Then the famous Barnard and Knill theorem tells us that the error using pretty good measurement is at most twice of the optimal error. In this case of discrimination between rho and sigma, the error using pretty good measurement is given by this, where 1/2 is a uniform prior probability. By using the cyclic property of trace, it is equal to this one. Then it is less than or equal to 2 times the optimal error, where the optimal error is just given by the Holevo-Hellstrom theorem by this. Then putting them together, you can see the trace inequality. So essentially, the lower bound to the trace non-commutative minimum can be viewed as an adaptation to the Barnard-Knill theorem. So here is our main result. For any classical quantum channel, there exists an n epsilon code with message size m and error probability epsilon, such that for any probability distribution on the input, the error probability can be upper bounded by this quantity. Here, the rho xp is the joint classical quantum state between channel input and output. To prove this result, I use the standard encoding strategy. Given each m, we construct a codebook containing m symbols x1, x2 to the xm, and then each symbol is randomly chosen according to some probability distribution px and pairwise independently. At this moment, you can consider all the cowords in the codebook are mutually independent. Then, the joint bipartite classical quantum channel state, classical quantum state is given by this rho xp. And note that the marginal state at the channel output is an average state. Okay, given a realization of the codebook, we have a bunch of states at the channel output to discriminate rho b x small m. Then the decoder is our good old friend, the pretty good measurement corresponding to this collection of states. It was studied back in 1975 by Belafkin, and it is defined by this. Okay, we are ready to prove the main result in the next slide. The error probability of a code is given by this, according to Bond's rule. Then we just use pretty good measurement and plug in the POPM element pi bx to get this one. Then the identity minus this operator can be written as this. Okay, Then now we focus on the trace for each x inside the sum. Okay, then use the trace inequality, the lower bound to the non-commutative minimum. We obtain the one with the non-commutative minimum. See what I'm doing? Let me take a step back. Using this inequality and filling the sum of the rate states as a whole operator, and then obtain the non-commutative minimum between the blue and the red. Okay, and then because we are using a random code book, we can take expectation over all x and x bar given x. Then right now, we move this rate conditional expectation inside to the second argument. This will induce an inequality because of the concavity of the non-commutative minimum, but we are in the right direction. See, so just move this inside. Then, by using the pairwise independence of the random code book, all the rate states in the second argument all become this marginal state will be because of the averaging, and they are n-1 minimum. Okay, and by using the direct sum structure of the trace norm, we are done. That's it. Okay, let me illustrate the whole procedure again in a graphical way. So at the channel output, we have a bunch of states to discriminate, and let's assume that rho bx1 was the send state. The critical measurement element for pi bx1 is deciding for rho bx1, as you can see the numerator, and its complement is deciding for the rest of the state. You can see the numerator. So a key observation is that the error of quantum state discrimination using critical measurement can be viewed as a bunch of errors of binary hypothesis testing between each rho bx1 and the rest of the states. So effectively, the critical measurement works as a one versus the rest classification strategy if you take this sum as a whole thing. Okay, we'll translate it to the optimal binary hypothesis testing using the non-commutative minimum. But note that this n-1 rest of the states depend on code book. It's hard to characterize them. But since we are using random code book, so we can take conditional expectation to average out all of the states in the second argument, so they all become rho B. So we can see why we like to use random coding strategy. It greatly simplifies the analysis and make our life much easier. Okay, in the end, since this x1 is also random, so essentially it's like we randomly pick a state, send it, and compare it to n-1 many marginal states. By the direct sum structure of trace norm, equivalently, we are comparing the joint state rho xb between input and channel input and output and the products. Again, this quantity is interpreted as the minimum error of discriminating the joint state rho xb at n-1 many product of the margins. Okay, then how tight is the bond? And what are the implications and the consequences of the result? See, this yellow box is the established one-shot bond. By applying the upper bound to the non-commutative minimum, namely the quantum channel bond, we can immediately get a one-shot exponential form in terms of Page-Renyi divergence. Then because the divergence is additive for product states, we immediately get exponential decay to the error probability in the IID setting for a fixed rate. We call this the large deviation result. If the rate is not fixed but approaching the channel capacity at a certain speed, the error still vanishes sub-exponentially. We call this the moderate deviation result by my early work with Min-Shu Xie. On the other hand, using the infimum representation of the non-commutative minimum, we get a lower bound to the largest message size. In terms of the hypothesis testing divergence, this gives the tightest achievable one-shot capacity so far. Using the second order expansion of the hypothesis testing divergence in the IID setting, we get a second order asymptotics for the rate. And this one mutual information is the first order, the information variance is the second order, and it's a 1/2 log n in the third order. Here, if the epsilon, the error probability, is not fixed but exponentially decays, we can recover the moderate deviation rate by using the result from Christopher Trapp, Marco, and Vincent Han. On the left side, all the existing one-shot bonds are sharpened. On the right side, the result implies all the three large deviation regime, moderate deviation regime, and small deviation regimes. Let me illustrate the asymptotic behaviors more. Here, the x-axis is the transmission rate. In the middle is the channel capacity. The y-axis is the optimal error probability. If you use channel only once, this may be the best error you can get. If you use channel many times in the IID setting, then all the error curves will concentrate to the step function. If you fix the rate and smaller than channel capacity, then the error probability will exponentially decrease. This is, we call it large deviation regime. If the error is fixed as a constant, then the rate will concentrate to the channel capacity at the speed of 1 over square root n. We call this the small deviation regime. Essentially, it is governed by central limit theorem. And these two corners correspond to the moderate deviation regime. So on the left side is the achievable region. So the established one-shot bond can cover all the three achievable asymptotic regimes in a unified manner. Okay, and moreover, the proposed analysis can lead to a variety of, can be applied to a variety of quantum information theoretic tasks. For classical communication over quantum channels with the assistance of entanglement shared between encoder and decoder, by using a position-based encoding strategy by Hao-Chung Chen and Wasi, and directly using the predicate measurement in the decoder, the proposed analysis immediately leads to an elegant one-shot bond. Again, the upper bound is interpreted as the minimum error of discrimination between the joint state between channel input and output, where this R is the reference system and the product of marginals. This achieves the state-of-the-art one-shot channel capacity. Okay, and other examples include broadcast quantum channels where we want to send messages from Alice to multiple receivers, Bob and Charlie, and also entanglement-assisted broadcast channels. Also, multiple access channels, we have multiple transmitters want to send their message to one receiver. And also entanglement-assisted multiple access quantum channels, and also classical data compression with quantum site information. Here, the goal is to compress the classical source into some index, but we have some help with the quantum site information. All of these achievability results can be succinctly summarized into this called the one-shot quantum packing lemma. They all use the predicate measurement at the channel output, and they will all have this similar form in terms of the non-commutative minimum. On the other hand, surprisingly, we realized that the proposed method is also useful in converse analysis for several quantum information theoretic tasks, such as quantum self-covering, complex splitting, privacy amplification against quantum site information, and quantum information decoupling. For the converse, we want to get a tight lower bound to the error calculated in terms of the trace distance between the processed state and the ideal state. I will not talk about this. Please refer to Tuesday afternoon for the talks by my student Yu-Chen Shen on privacy amplification, and also for the talk by Li Gao on joint state channel decoupling and one-shot quantum coding theorem. Okay, in summary, the proposed simple analysis is different from the information spectrum method. It's quite generic and versatile to many problems. It also holds for infinite dimensional Hilbert space as well. For bounding the message size, the proposed method could potentially achieve the best third-order rate if there's no specific assumptions on the channels. For bounding the error, I believe there's still room for improvement because the best error exponent is not achieved yet, so this problem is still open. With that, I will thank you for your attention.
Thanks a lot, Hao-Chung. Yeah, questions?
Thanks for great talk. At the moment, you're applying this technique of pretty good measurement for basically encoding classical information. And in the end of the talk, you're talking about decoupling. What's the difficulty in applying this kind of technique to decoupling and state merging or this kind of quantum tasks?
That's a great question. Yeah. So,
the challenge here.
This analysis can be applied to many protocols, like in a communication setting. But for example, for quantum state merging or quantum decoupling, turns out that this method is useful in the converse. So it's in the opposite way. I think I would say that it's also useful, but in different directions. So for communication problems, this method is used for achievability, meaning the upper bound to the error probability. But for quantum decoupling or state merging, it'll be useful for getting a lower bound to the error. So it's opposite.
Okay. Thank you very much.
Thanks, Ayana.
Hi. I have a question regarding the pretty good measurement. We know that the pretty good measurement does pretty good in the sense that the optimal error probability is the error probability for the pretty good measurement is not more than twice the optimal error probability.
Yes.
I believe that it is for discrete variable and finite dimensional systems, and we can also define the pretty good measurement for continuous variable systems. Is there any such special property for the pretty good measurement for continuous variable as well?
Okay, so you are talking about is continuous in input or output?
What is that?
Input or output? You want to discriminate infinite many states or?
Well, we have an ensemble of
states.
Let's say it has a continuous parameter. Say parameter is on Rn, and the states are in continuous variable systems, and we can define the pretty good measurement using the mathematical description, the canonical form we have.
Yeah, so it's integral, right?
Yeah.
The denominator is integral.
Yeah, right.
Okay. So in this case, let me think. Okay, I think the bound and continuous theorem, they only prove for the discrete input case, and I'm actually not sure if their result can be applied to the continuous case, but I do believe so, because if you follow the proof, they just use Cauchy-Schwarz inequality or some data processing inequalities. If you can handle some measurability problems because you have an integral, then I think it can be done.
Yeah. I mean, when we have only finitely many states, then it makes sense to talk about the error probability there. Yeah. But I'm not really sure when we have the
infinite.
If the ensemble is like continuously spread, then what is like? How do you define the error probability? Like, what is? I'm not really sure what comes there.
In the classical case, yes, people already did that. They just use some measure theoretic arguments to define this pretty good measurement in the classical case. So in the classical case, yes, that has been done. In the quantum case, I'm not so sure, but we can also use the measure theoretic argument there.
Okay, thank you.
Thank you. Any more questions, discussion? Yes, there, please.
Hello, thank you for the presentation. First of all, thanks for the really pedagogical way of explaining the proof. I thought that was really cool. I had a question about the small deviation regime.
Yes.
Where I believe you obtain a lower bound. Could you also obtain a lower bound when you have the expansion of the achievable rate?
Yes.
As a function of epsilon and n?
Yes.
Yes. Do you also have an upper bound?
Okay.
Here, that matches, that has the same.
Okay, that's a good question.
Thank
you. Backup slides for this. So in this talk, I only consider the achievability part for classical communication of quantum channels, and the converse part was already been done by William Matthews and Stephanie Werner. So in their IEEE transactions paper, they got some, I think it's already very tight one-shot bonds. So here is my result for classical communication of quantum channels without entanglement assistance. This is with entanglement assistance. Then they show for these two cases both the converse bonds, also in terms of the hypothesis testing divergence. So we can say that we already obtained a nearly optimal one-shot characterization for those quantities. And you just need to use the second-order expansions by Marco, Hayashi, and Curry to expand those DH. You can get a matched second-order bonds. And in this work, my one-shot achievability bond will lead to better third-order rate. Does that answer your question?
Thank you.
Okay, one last question or? Okay, then I hope I didn't miss anyone, but thanks for the discussion and Hao-Chung again.